I can push the pointer slowly from 0 to 9. And the output voltage approximately follows. Hi, I'm Kevin. Welcome to my cave. Quite a while ago on the channel, I posted a video introducing the op-amp integrator. I did that before I started the series on op-amp basics, but I'm adding it to the playlist here. Today, I'd like to examine the integrator's flaws and how to improve its performance. Once we have a decently precise one, I've also got what I think is a fun idea to show it off. I hope by the end of the video you'll agree, and maybe favor me with a subscription. In case you didn't watch the earlier video, let me do a quick review. The integrator, as the name suggests, outputs a signal proportional to the integral of its input voltage over time. It makes a square wave into a triangle wave, a sine wave into a cosine, a ramp into a series of parabolas, and so on. We started by looking at the RC filter and how it's almost an integrator, provided that its output signal is tiny enough and the time of integration is short enough. Otherwise, of course, it will simply turn into a mess, because any voltage already stored in the capacitor will limit the input current. The output will be inverse exponential rather than linear. We fixed that by putting the integration capacitor into the feedback loop of an op-amp circuit, with the input resistor going to a virtual ground. The current in the capacitor must balance the current in the input resistor, and feedback is holding the op-amp input at a virtual ground, so the output voltage should be ideally proportional to the integral of the input voltage. But when we actually tried it, we found that the circuit ran away. The output voltage keeps on drifting right to one supply rail or the other. Because we're dealing with a real op-amp, it doesn't hold its input voltages exactly equal. There's a small offset voltage. If we ground the input, there will still be a small current through the input resistor, which will continue to charge the integration capacitor. The output voltage will continue to drift right up to the supply rail. We found several ways to control that. We could add a feedback resistor to keep the DC gain finite. We could add a switch to reset the integrator at the start of the time interval. Or we can try to mitigate the effect by using an op-amp where the offset voltage can be trimmed. The feedback resistor makes the output voltage droop, which makes the circuit useless at long integration times. The reset switch adds complexity. The circuit needs to provide a logic signal to make the integrator reset at the right times. And the trim adjustment adds time and annoyance to get the circuit adjusted and may not be temperature stable. And that's where we left off, with an integrator that's good enough at audio frequencies but can't reliably go much slower. Before we continue, let me interrupt for a few moments. My videos are always free to all comers. Nothing is ever paywalled, and I don't waste your time selling various dodgy products. But I do end every video with a plea that you take care of one another. To this end, all the channel's ad revenue has gone to charity. This month's featured recipient is Médecins Sans Frontières, Doctors Without Borders. MSF is an independent international organization that offers medical humanitarian aid to people based solely on need, without regard to race, religion, gender, or political affiliation. It provides over 10 million consultations annually in more than 70 countries, including some of the regions most torn by violence, neglect, or catastrophe. And it trains health workers and invests in local infrastructure to meet healthcare needs sustainably in a community-driven way. I'm asking my viewers to join me in supporting this organization. This is a small channel, so I've set a modest goal of $500. Those $500 could provide 2 treatments to cure patients of hepatitis C, 4 resuscitators for non-invasive ventilation in newborns, or enough vaccine to immunize nearly 1,400 children against measles during a deadly outbreak. We managed to meet our goal in the last fundraiser, so I'm sure that my wonderful viewers can get us there again. Won't you please join me today? Thank you so very much. Now that we understand op-amps better, I want to look at integrators in more detail. They are challenging to get right because they tend to expose all the flaws of op-amps. Every problem gets integrated over time, so every problem gets magnified. I'm going to start with a simple integrator built out of the venerable Micro A741 op-amp. I'm doing this to exaggerate some of the possible pitfalls. While the 741 was wonderful in its time and is still marketed widely, its time is long past, and now I mostly use it as a bad example. I'm going to put in both the feedback resistor and the reset switch to start with. I'll start the integrator up and feed it with a 1 kHz square wave. And it doesn't work even with the feedback resistor. I hit the reset button, and the correct waveform shows up momentarily, but it immediately heads off into outer space. I can bring it back by dialing in an offset voltage on my AWG. But it's not stable, and clearly we don't have to monkey around with offset voltages all the time. There are two effects in play here. One is the input offset voltage, which we saw in the first episode on integrators. The other is the input bias current, which we saw in the episode on the sample and hold circuit, where it drained the hold capacitor, causing the output voltage to droop. I want to try to tease these effects apart. Let's remove the feedback resistor to knock out its stabilizing effect. Now there's nothing but the reset switch stabilizing the circuit, and the voltage drift is even faster. To simplify things even more, I'm going to disconnect my function generator and just leave the input open. There won't be any input current that can be attributed to the offset voltage, since that would all come through the input resistor, which now isn't connected to anything. That leaves the input bias current as the only thing that will charge the capacitor. We know what a constant current will do to the capacitor voltage, so if we measure how fast the voltage drifts in this configuration, we will be able to solve for the bias current. Let's set the scope up to measure a slow drift and see what it shows. The output starts a slow but inexorable climb toward the supply rail. I won't make you wait for it to finish. Once it's done, I'll set scope cursors to measure how fast it's climbing. 10 volts in 25 seconds times 100 nanofarads. The bias current is about 40 nanoamps. That sounds tiny, but it's obviously too big to ignore. I'll come back to what we can do about it. Now let's ground the input instead of hooking it to the AWG and repeat our measurement. Now there are two currents charging the capacitor: the input bias current of the op-amp and the current through the input resistor. Since we know the bias current, we should be able to determine the offset voltage. This time it's drifting much faster. 10.24 volts in just 10 seconds. Multiplied by 100 nanofarad, and now the capacitor is charging a little over 102 nanoamps. Subtract out the 40 nanoamp bias current, and there must be about 62 nanoamps flowing through the input resistor. Multiply by its value, 22K, and it looks as if our op-amp has an input offset of 1.37 millivolts. These effects are wreaking havoc upon circuit stability. But what can we do to tame these effects? Let's look at bias current first. Bias current has little effect on the behavior at signal frequencies, so we care only about DC. We can ignore the capacitor and the reset switch, and consider only a fixed input voltage. This circuit is a simple inverting amplifier. If it weren't for the bias current, the output voltage would be negative R2 over R1 times the input voltage. Can we make that equation hold in the presence of the bias current? Well, let's look at what happens if the input is grounded. If the equation holds, the output will also be at ground. So what's the voltage going to be at the op-amp's input? These two resistors are a parallel combination, and Ohm's law tells us what the voltage has to be. Now we need the same voltage at the positive terminal of the op-amp. And we can get that voltage easily. Put a resistor equal to the parallel combination in series with the positive lead. It will also pass the bias current, and therefore it will drop the same voltage. That's all there is to it. You can either grind through the algebra or use superposition and find that for any input voltage, we've cancelled the bias current. And that stays true even when we factor in the op-amp's offset voltage. For our integrator, R2 is so much bigger than R1 that we can safely ignore it and just make R3 equal R1. So I'll do that and try the test again. I won't make you wait for it. The drift has slowed to 10.48 volts in 17 seconds. Multiply by 100 nanofarad, and now the capacitor current is about 62 nanoamperes. That's exactly what we calculated before for the contribution that the offset voltage made to the capacitor current. So we've successfully cancelled out the bias current. By the way, equalizing the impedances seen by the two op-amp inputs is a good idea in any high-impedance circuit with high DC gain. FET input op-amps often let you get away without worrying about it, because their bias currents are often down in the picoamps. But you still may need to watch out for thermal effects. The bias current of an FET input op-amp typically doubles with every 10 Kelvin of temperature. And that's the chip temperature, not ambient. So be especially careful if your op-amp is called on to source or sink high currents. Dealing with the offset voltage is another matter. Generally speaking, if offset voltage is a problem, we have to use a lower offset op-amp, or at least use some sort of trim to null the offset. For trimming the offset, the 741 datasheet suggests a 10K pot between pins 1 and 5, with the wiper going to the negative supply. I'll try that. Then comes the fiddly process of adjusting the pot until the drift is as slow as I can make it. That usually consumes at least a couple of minutes. I think that's about as good as I'm going to get. It appears to be drifting almost randomly both up and down, but at no more than about a millivolt a second. Now I'll put the 10 meg feedback resistor back into the circuit. The output at least stays near to ground, but it's not stable. It glitches up and down. I don't think this will quite do for an LFO. You're likely to see similar results, by the way, with any super cheap bipolar op-amps, like the LM321, LM358, and LM324. This is just not a job for the cheapest op-amps on the market. Let's move on then to my personal workhorse for a single op-amp, the JFET input TL071. I'll do the same drill. First off, I want to measure the input bias current. When I open circuit the input, the drift slows to where the scope is pretty useless. I'll resort to stopwatch and millivoltmeter. The output drifted 8.18 millivolts in 20 seconds, or 418 microvolts per second. Multiply by the 100 nanofarad integration capacitor, and that's a bias current of 42 picoamperes. That's nearly 1,000 times smaller than the 39 nanoamperes of the LM741. This is one of several reasons that I prefer FET input op-amps for general uses. I'll ground the input to test the offset voltage. I already have stopwatch and meter set up, so I'll just use them. Without trimming, it's drifting about negative 170 millivolts a second, which calculates to an input offset of about 370 microvolts. That offset is about 4 times better than the untrimmed 741, but clearly not good enough. Now comes the job of trimming it out again. This time the manufacturer recommends a 100K pot connected to the negative supply through a 1.5K resistor. But I know from experience that arrangement is too sensitive, so I'll use a 10K pot between two 47K resistors. I'll spare you all the fiddling, but I got to where the drift was well under a millivolt per second. But there's another trouble waiting in the wings to bite us. Watch what happens if I give the chip a tiny bit of warm air. This isn't really hot air. My heat gun is on its lowest settings of both temperature and airflow. Even with offset trim, making a long-period integrator temperature stable is a real challenge. Isn't there anything more that we can do? It turns out that there is a way, and it's a really clever idea that goes back to the vacuum tube era. It was first described in a 1949 patent and a 1950 paper by Edwin Goldberg of RCA. I won't go into all the details of Goldberg's design, which of course used single-ended vacuum tube amplifiers, and even used an electromechanical chopper switch to switch rapidly between two signals. Instead, let me show how a modern IC does it. We'll be using a circuit with two op-amps, but they're a little different from the ones we've been working with. They have an extra terminal, called the nulling terminal. In effect, the nulling terminal is another input, and it's often implemented by adding another transistor to the differential pair at the op-amp's input. The op-amp can be built with the nulling input either inverting or non-inverting. Analyzing the op-amp open loop, the voltage of the op-amp's output will be some open loop gain, A, times the differential voltage, plus an offset error. Then there's another term, that's the contribution from the nulling input. As with any op-amp, the gain A is very large, always at least in the tens of thousands, and often a million or more. With that out of the way, let's start looking at the clever solution to the offset voltage problem. It looks kind of complicated at first, but it's not as bad as you might imagine. Let me walk you through it step by step. First, here at the bottom, we have an oscillator that's generating a logic signal at a relatively high frequency. It's toggling a double-pole, double-throw analog switch rapidly between the up and down positions on the diagram. We'll begin our analysis with the switches in the down position. With the switches in this position, you'll see that the two inputs of amplifier A1 are being held equal, and the inverting nulling input of amplifier A1 is tied to the amplifier's output. The equation of the amplifier's output depends only on the amplifier's offset voltage. We can bring the output voltage term over to the left side of the equation, and then we note that the amplifier gain is about 1 million, so we can ignore that unit term. Amplifier A1 is measuring its own offset and storing it on the left-hand capacitor. Now the clock ticks and the switches flip up. The capacitor is now holding amplifier A1's offset voltage. A1 is now canceling its own offset and amplifying the difference between its inputs nearly perfectly. The right-hand capacitor is storing that amplified difference voltage, and we're presenting it to the nulling terminal of amplifier A2. Now we can look at what amplifier A2 is doing. We write out the equation for its response. Note that the nulling input is non-inverting on this amp, unlike the inverting one on amplifier A1. We substitute in the formula that we derived for the voltage at the nulling terminal and rearrange the terms. What we get is that the circuit as a whole in this phase behaves like an amp with an open-loop gain that's the product of the gains of the individual amplifiers, and an offset voltage that's amplifier A2's offset voltage divided by amplifier A1's gain. That offset voltage is nearly negligible. The op-amp's offset voltage has to have been small to begin with, and we divided it by 1 million or so. And we have one more trick up our sleeves. When the clock moves the switches back to the down position again, the right-hand capacitor is continuing to hold the same offset voltage. No voltage is changed at amplifier A2. The two input voltages are the same, and so is the nulling voltage. The output voltage therefore has no immediate change. We've therefore set the nulling voltage to be exactly what it has to be to correct the input offset of amplifier A2. And op-amp offsets change relatively slowly, so A2 should maintain its low offset until the next clock cycle. There's nearly zero offset at A2 on both phases of the clock. The open-loop gain during the auto-zero phase will be perhaps 1,000,000 times lower, but negative feedback will still function to keep A2's inputs nearly equal. This configuration is so very useful that all the major manufacturers offer ICs with this whole circuit inside. There are a bunch of names for it. Auto-zero or commutating auto-zero op-amps, zero offset or zero drift ones, and some manufacturers even call these op-amps chopper stabilized. But you have to watch out for that name. There's another circuit also called a chopper op-amp that uses a different circuit topology to try to stabilize the offset by separating AC and DC signal paths. I'm not going to get into that one here. They're wonderful for certain things. They have nearly no offset voltage and nearly perfect common mode and power supply rejection. They also don't have any flicker noise, which causes transistor circuits to drift around randomly at extremely low frequencies, for instance less than 1 Hz. But nothing comes for free. They're relatively noisy, particularly at the clock frequency and its harmonics. Their input bias current is higher than you might expect, as much as half a nanoampere for some devices. Their slew rate and settling time are quite slow. You have to be careful not to let them swing all the way to the rails because their saturation recovery time is positively abysmal, often a few milliseconds or more. They're best used where you need slow but accurate measurements. Things like weigh scales, strain gauges, current shunts, and thermocouples love them. They're also great for DC conditioning, as when you want to derive several voltages from a single bandgap reference. And they're okay for any application that can tolerate some broadband noise but needs low offset or low drift. They're less expensive than premium quality op-amps with factory-trimmed offset voltages, and less work than trimming an op-amp manually. Let's see one in action. I've chosen an OPA 186 to test with. That's my current favorite part for this sort of application. It displaced the classic LTC 1150 a while ago. It's not inordinately expensive. It's one of the few zero offset op-amps that will run off plus or minus 12 volt supplies. Its input and output both can go to the power rails. That's convenient. The datasheet says to expect a typical offset voltage of 1 microvolt and a max of 10. The drift is only 10 nanovolts per Kelvin. That's not something that's actually going to be achievable in practice without some pretty heroic board layout. A typical board has junctions that act as thermocouples and will totally swamp that tiny voltage. The input bias current is pretty good. Typically only 5 picoamps at room temperature, and only about half a nanoamp over the entire temperature range. And the manufacturers have actually managed to tame the noise quite a bit. I did want to look at how bad the noise is in practice, so I hooked the op-amp up as a gain of 100 amplifier, with a 10K input resistor and a 1 meg feedback resistor. When I looked at the output with the input grounded, at 200 microseconds per division on the scope, I saw it alternated up and down, according to the position of the switches in the internal circuit. The alternations were at about 5 kHz, but seemingly random. I'm sure the manufacturer intended this. Low-intensity broadband noise is usually more tolerable than a 5 kHz tone. By the way, when you're doing noise measurements, it's always a good idea to compare the behavior with the power off, because the noise may be leaking into your circuit from outside. At this frequency, the outside world looks to be innocent. By comparison, at the power line frequency, we're seeing some fairly large excursions, totally swamping the broadband noise. These get smaller with the power off, but by a factor of less than 2. The gain of 100 amp is amplifying the power line noise by much, much less than 100. All of these effects are at only a handful of millivolts, so I'm not going to worry too much. Okay, let's put this thing through its paces as an integrator. I'm simply going to skip the basic offset and bias tests because the datasheet parameters look so good. Instead, let's try something fun. I have here a little permanent magnet motor that I got off of AliExpress. Like any permanent magnet motor, it can be run as a generator. If I twist the shaft, it'll put out a small voltage. If I twist it fast, the voltage will be relatively large. If I twist it slowly, the voltage will be proportionally small. If I twist it in reverse, the voltage will be negative. If I integrate these voltages, I should be able to keep track of the shaft position. I've stuck the motor shaft through a hole in the lid of a cardboard box. Then I've attached the motor and the box to a ring stand using a little piece of scrap wood and a couple of woodworker's clamps. Turning around to the other side of the box lid, I've put a pointer on the motor shaft. It's just a zip tie, hot glued to a little piece of scrap vinyl tubing that can press onto the shaft. The pointer is running on an inkjet printed scale, spray glued onto the cardboard. I'll feed the motor voltage into an integrator, built from the zero offset OPA 186. I'll wire it just the same as the other integrators that we've been looking at, except that the input resistance will be about 16K with a trim pot, instead of the 22K we've been using. It's even uglier than the typical kludge from Kevin's Cave. But it'll show the approximate shaft position. Really inaccurately. The pointer isn't stiff enough, and I'm not 100% positive that the press fit isn't slipping. And there seems to be backlash somewhere. But I'll zero the pointer and reset the integrator. And have my helper hold the wire in place there. I've trimmed the integrator's input resistance off camera to make the voltage at the integrator output approximately match the scale. I can push the pointer slowly from 0 to 9. And the output voltage approximately follows. Or I can turn it back real fast, and it comes back approximately to 0. I can move it suddenly to some other position on the scale, and the meter tracks whatever I do. Of course, I can return it slowly to the point where we started. If I had trouble to print a negative scale, I could read out down there too. And returning it to 0 returns the output approximately to 0. Everything is a little nonlinear. I bet that if I had a more careful setup and logged a bunch of positions, I could find the poles of the motor. This particular demo is totally useless, of course, but it shows that I have an integrator that would be useful in a low-frequency oscillator or envelope generator and be able to do things like control a musical crescendo over many seconds. And I hope it gives you ideas about how you might use a precise integrator in your projects. Let me know in the comments what you come up with. I'd love to hear about it. By the way, the first time I tried this, it drifted like anything. I built the OPA 186 integrator on the same breadboard as the 741 one, and I was careless about the layout with ground strips on both sides of the breadboard. Even worse, I connected the motor to one side and the non-inverting input to the other. The 741 is kind of a pig. It draws a couple of milliamps of quiescent current. One ground rail was carrying the ground current of the 741, while the other wasn't. That gave a few tens of microvolts difference between the two sides of the board. That was enough to make an insane amount of drift in the integrator. Proper layout is really important in a precision circuit, and I'm pushing solderless breadboards farther than they're meant to go. Moving the integrator to a breadboard by itself, it worked all right. To summarize, in this episode, we've seen many more details about the op-amp integrator, and improved the integrator we had in our triangle wave oscillator into one that's stable over many seconds and can integrate small signals like the backward voltage from an electric motor. We learned about the effect of input offset voltage and bias current, and what to do about them. And we took our first look at zero offset, zero drift op-amps. Next time, I want to undo what an integrator does, and look at its opposite, the differentiator. I hope you'll stay tuned for that, and maybe ask the YouTube algorithm to tell you when it comes out. Until then, stay safe, stay healthy, stay curious, and take care of one another. Bye!